Good night, everyone. Mechanics of Materials, Chapter 5 Torsion. We want to review torsion in continuous torsional torque. So we want to see the effect if we having like a continuous torsional torque applied all over the entire length of the beam. What would be the uh, torsional torque effects on the free end of the beam? So we all already know about if we have a circular cantilever shaft like AB attached to a fixed support at A and free at the other end and apply a torsional torque like T. The angle of twist is torsional torque phi is T torsional torque times the length of the beam over shearing modulus of the shaft times polar moment of inertia. Now let's see what if a continuous torsional torque applied to a beam like figure in the below. So in this case, phi at the free end is a small t L squared over 2gj. Let's see how we can derive this equation. So we want to calculate phi at free end at a free end of a continuous torsional torque on a cantilever shaft. So if you just consider a distance of x and consider an elementary form of angle of twist is d phi, and that's t times x by the length of our travel over gj. And then if you want to get the angle of twist, that's the integration all over the entire beam, shaft, and time. And it just gives you integration of 0 to L tx dx over gj. And if you do the math, it just gives you a, a small tl squared over gj. And if you consider the small t times the entire span like capital T, you can jot down or rearrange the equation like TL over 2GJ, what we were looking. So for the previous part, if there is a single torsional torque, that's the angle of twist is TL over GJ, and it's a continuous one. Angle of torsion is TL over 2GJ. We'll discuss it further. Let's flash back to axial deformation or elongation. Just consider the same a circular solid shaft attached to a fixed support, and you are applying a force like W over 2. The axial elongation, if you remember the axial deformation or elongation, the equation delta was FL over EA. So let's just flip-flop the uh, our shaft like by 90 degrees and then apply the force of W over 2 at the other end. And that says if there is an overhanging shaft under its own weight, it just seems as if we are replacing distributed load of W with a concentrated load of W at the free end. So for this case also delta is FL over EA, and if you replace F by W over 2, that's a WL over 2EA, exactly like a axial deformation. The same story applies for torsion. So for axial deformation, again, we say if there is overhanging solid circular shaft under its own weight, you can remove the weight and add it like a half of that weight at the free end, and then W delta is of the effect of WL over 2EA. That's the axial deformation. The same story applies to angle of twist under a continuous torsional torque on a solid circular shaft in a like in cantilever. So phoebe, we already calculate this formula by integration. That's a small TL squared over 2GJ. And you can also write it down like TL over 2GJ. You can easily see the effect of delta in axial deformation is W over 2EA, and phoebe under the continuous torsional torque is TL over 2GJ. And then again, this is the effect of a single torsional torque phi is TL over 2GJ. For a continuous one, it just gives you 2 TL over 2GJ. Thank you.